Welcome, everyone. Good morning, good afternoon, good evening to our global audience. My name is Judy Sharman. I'm the Operations Manager for the Instrumentation and Measurement Society. On behalf of President Salvo Balio, we welcome all of you to the I&M Virtual Distinguished Webinar Series. Before we get started with our speaker, I just want to give a very brief introduction to our society. As you can see, our field of interest is the science, technology, and application of instrumentation and measurement. I encourage you to go to our website at IEEE-IMS.org and investigate our activities and initiatives and see where you can become involved. There's a place on our website for you to join the society, and we would just welcome you to join us. And we hope to see you at one of our conferences in person in 2022. And now, without further ado, I want to introduce our speaker for the day, Dr. Daniel Watzenig. Dr. Watzenig is at the Institute of Automation and Control in Graz, Austria, and at the University of Technology. He's a full professor of autonomous driving. He is also involved in publications. He's the EIC of the SAE International Journal on Connected and Automated Vehicles. He's also an invited lecturer at Stanford University in the US. And the coolest point, I think, here is he's the founder of the Autonomous Racing Graz team in the Global RoboRace race series. We're so happy to welcome you, Dr. Watzenig, and take it away.
Yeah, many thanks, Judy, for your kind words, for your introduction. Yeah, great to have the opportunity to give a talk today during, let's say, the online sessions, the online webinar of our society. And I'll share my slides in a minute. Here we go. Just get them in presenting mode. Right. So what I'm going to present today, and would be happy to discuss afterwards, is there has been, let's say, quite a time where autonomous driving was really a hype topic. It's still a hype topic, but today let's have a look where we are right now. What are still the remaining challenges? What is the progress, and what are recent advances? Just to look at right now, September 2021, where we are. That's actually the idea of today. And what I've planned for the presentation for, let's say, the next 45 minutes actually is to give you a short introduction to autonomous driving, because I'm aware that not everyone is, let's say, fully into this topic, although there are so many news, so many media articles, but I just would like to make sure that we're on the same page. Then I would like to give you a bit of where we are right now. What is the state of play? What is the state of practice? And to get, let's say, to have also a bit of a deeper look, I would quickly and briefly revisit the autonomous driving architecture, where, let's say, the main technical issues what we still have to face, and having a bit of a closer look to the perception layer, which is the most important one, because that actually is how to perceive the environment, how to make sure that an autonomous car is actually able to replace us as human drivers. And giving a bit of, let's say, an outlook, what are the challenges, what is still there, but what has to be solved, where we come into play, all of us, all researchers and developers around the world. And and give you, let's say, a bit of what are the next steps, what do we expect from autonomous driving? If we just look back, what has been stated some 6-7 years ago, and that's still valid. It's still there, that the benefits that we actually expect from autonomous driving are, let's say, manifold. And we have the issue of safety. We know we have a lot of road fatalities every year in every country in this world, and autonomous driving could actually reduce this number of road fatalities. That means we could actually improve safety. Secondly, we are living in a climate change. We have the Green Deal in some, let's say, countries. We are all part of this process that we see that we have more thunderstorms, hurricanes, floods, whatever. That means the automotive industry could actually contribute to that. And it means reducing energy and emissions is one important thing. And if you just look at two use cases, the first thing what I'm actually meaning is aerodynamic drafting is the topic of platooning. If we have just one driver and we form platoons, the big trucks are, let's say, are driving in one line, they are queued up. That actually means that we actually could work out that if the platoons, let's say the trucks are driving within 7 to 10 meters, so just a couple of yards, that we can drastically reduce the emissions due to this aerodynamic resistance that we actually optimize. Then let's say that's common sense, that autonomous driving goes hand in hand with electric cars. It doesn't make sense to do the retrofitting of, let's say, of combustion engine driven cars. It makes much more sense to focus on electric cars and automate those cars. Then another huge benefit is in the mega cities, in the big cities where we have a lot of traffic jams, especially in the rush hours, that we actually could improve the traffic throughput. That means we could, when talking to the signaling, that means to the traffic lights, that we could improve the traffic throughput. Another thing is with autonomy, we could actually support this mobility as a service, MaaS, which is, let's say, an acronym which is meanwhile well known, that we have, even if we have different modalities, that means the train, electric bus, autonomous cars, that we actually could come up with, if you would like to go from A to B, and you get basically the energy optimal solution to that. That is in your, let's say, looking on your own perspective, autonomous. That's another thing that allows, if we have autonomous cars and people movers around, that means we could actually support this mobility as a service approach. And finally, that means if we have, let's say, the autonomous cars around, we could actually bring elderly people or handicapped people back to mobility. That means it's a huge benefit, because we all know if we have no issues with mobility is great to have, and the other way around, if you don't have mobility anymore, it's a huge issue that you actually face, and bring those share of people back to mobility is also a great issue forward. And in the end, it's all about comfort, efficiency, and safety. It's not the same share, but we'll see later on where let's say, the benefits when it comes to autonomy and, let's say, in the field of comfort, efficiency, and safety. Before we go a bit in the state of play 2021, I think it makes sense just to briefly review what is autonomy, what is, let's say, the classification, what is the categorization of autonomy. And back in 2016, the SAE, the Society of Automotive Engineers, they came up with the G3016 levels of driving automation. And maybe one side comment there is, although we all use the word autonomous or autonomous driving, just looking at, let's say, at the official naming, it's automation, because automation always means we as humans automate something, while autonomy means that the system itself decides and comes up with, let's say, proposals and decisions, and we might, as a human, not be able to influence anymore. That's just the formal difference between automation and autonomy. Of course, autonomy and autonomous driving is much more catchy than automated driving, which is a bit more, let's say, a bit more, I would say, in my world, it's a bit of a hard to pronounce, typical German, Austrian, English, automated driving, while autonomous driving is much more fluent. But looking at the slide, we have the blue part and the green part. The blue part always means that the human is in charge. And that actually means those cars are already on the market. We have level 2 cars on the market. We have still level 1 and level 0 cars on the market. The best example for a level 2 car is the Tesla. So all brands, let's say all variants of the Tesla brand are level 2 cars. Let's say the more more sophisticated and even more expensive cars are typically level 2 cars, while I would say the mass of the cars are level 1 cars. And you see, just looking at the lower part of this block diagram, that for instance, level 1 means that we have lane centering or adaptive cruise control. That means either or. We have, let's say, lateral control or longitudinal control, while level 2 actually means we have both, and that actually means that we have lane centering together with adaptive cruise control, and that's the autopilot of Tesla, for instance. But still, the human is in charge and is more or less responsible for the car. And then we have the green part, level 3, 4, and 5, where level 3 is, let's say, a bit of a specific one. It's viewed in different ways, but in the end, level 3 was always planned for highways. Level 3 means that the car, and we have a certain human-machine interface. That means the car can actually hand over the control to the driver and backwards. And a lot of discussions arose over the years. What happens if we have an emergency situation and the car is not able to deal with that, and suddenly the driver has to handle the situation, just stopping reading emails or stopping the phone call and let's say taking over control. That was never meant. It was always the idea of level 3. You drive manually on the highway. Once you're on the highway, you hand over the control to the car. And once, let's say, a couple of, let's say, seconds, 10 seconds, up to 20 seconds, when you're going to exit the highway, then the car gives you a reminder. Please make sure within the next 15 seconds, take over the control, put away your laptop, your tablet, whatever, take over, and we need to exit. That was the original idea of level 3, and that's still valid. And all the other, let's say, fancy ideas of suddenly in heavy rain, the car says to you, take over, I'm not able to see anymore, my sensors are not working. That was never the plan. But let's say in the general discussions, it always comes up, this kind of level 3 discussions. Anyway, level 4 is the one which is the most interesting one. Level 4 means we as a driver are out of the loop. There is no blue column anymore in this level 4 situation. And level 4 and level 5, the only difference is level 5 would actually mean the car is able to deal with any situation, regardless where we are, what we are doing. So the car works quite well in New York City, in Mumbai, but also in the countryside somewhere in Australia, in the bush. And you could imagine that's let's say there are horrible requirements for the technology, and that will never happen. To be honest, that's my opinion. We are far away from that, and I think that will not work at any time in the future. That we are able to build a system that can manage any situation that might appear. And level 4 actually means the reduction of level 5. And the reduction actually means we define a certain operational design domain, ODD, operational design domain. And that actually means we are just driving on the highway or just during daylight or only in the city and at a certain speed limit. And we are not allowed to exceed the speed limit. So we are, let's say, shrinking the operational design domain, and that makes it more easy. for instance, on the highway, we don't have to deal with bicyclists or pedestrians. That makes this it's more easy for the car manufacturers to come up with solutions. So level 4 is the one that is discussed everywhere. Level 3 on the highway, and level 5 is it's a bit of a fiction, to be honest. If we just look at a bit the regulations, and I just got the slide, which is 3 years old or 2.5 years old, that actually reflects which countries are very active in autonomous driving. Of course, it's the US. It's let's say certain countries in Europe like France, Germany, UK, and Sweden. It's let's say the correlation is pretty easy. Where car manufacturers are placed or located there, the topic of autonomous driving is pushed. In other countries where you don't have car manufacturers, or tier 1 suppliers, it's not that pushed anyway. So that's the situation in 2018. We got a lot of tests. We have seen that, for instance, just looking at the miles driven in the US, especially in California, Arizona, and Nevada, they were really great. A lot of data has been collected by Waymo and all the others. It was actually fantastic to have, let's say, all this data there to advance the technology. That's 2018. What happens, or let's say what happened now in the last couple of years, basically, there is, when just looking on the legal situation, the Department of Transport in the US, DOT, of course, is very active, and we have seen a lot of, let's say, incremental improvements when it comes to legal issues. For instance, a safety driver is not anymore required, especially in Arizona, Nevada, and California. And there is, let's say, a clear way forward. There is, let's say, a common understanding paper in the US, which is public available, that can be downloaded from the DOT, where you can actually see the strategy of the US. And the other country that pushed it from a legal part pretty much is Germany. Germany is actually right now the first country that comes up, and actually you could say it came up with a solution, because this new regulation, this legal regulation, is in force since the end of July, where you could actually run autonomous cars on the road, and it's clearly defined what happens if there's an accident. Who is in charge for the liability? That's all there. Germany pushed it quite much. Of course, Germany has a couple of strong manufacturers, and they push that to have the legal, let's say, the legal framework there. Yeah, but the question still remains: how close are we to self-driving, to autonomous driving? And if we just look back to 2015 and 16, let's say many brands actually announced we will see highly automated driving in 2020, so last year, and nearly fully automated driving, even level 5, in 2025. Meanwhile, we know technology is not that mature that we expected. We still have especially issues, and I will come to that later on, with the perception, with the sensors, to really replace us as human. And just listed a few statements of GM, Ford, and Toyota from this year and last year. And you actually see we have to go a little bit back, and all of those big brands, they actually now have to adapt the overall strategy. And the overall conclusion is it was a little bit of an overestimation. Back in 2015 and 16, we expected much more to be able to buy those level 3, level 4 cars in 2021, which is actually not the case. And yeah, we are not as close as we thought. That's more or less the conclusion from those three statements we've just seen before. But the question is, how far are we? And if we actually look once again to our levels, level 0 up to level 5, of course, level 0, level 1 is not that interesting. Level 2, as I said, that's the Tesla. So that's that's the approach we are currently following, level 2, and people actually, well, let's say different companies actually say level 2.1, level 2.8, 2.9. So there is a bit of a, let's say, a granulation there. Level 3 only makes sense on highways, as I mentioned before. Level 4 is in the focus, and level 5 is just too far away. It's just not feasible to come up with a solution that works in the desert, quite same let's say in the same quality as in a mega city. That will not happen. So level 2 and level 4, that's the focus. And if we, and I will come up with an example in a second. If you look on the level 2 car, and I just took the Tesla because that's the most famous car, which is a level 2 car around. And the Tesla actually focuses on the camera approach. Although there are ultrasonic sensors, radar sensors, the IMU, which is the inertial measurement unit with the acceleration sensors, and GPS is also there. But Tesla actually follows the camera approach. And that's pretty fine for level 2. For level 4, the example is Waymo. Waymo actually, right now focuses on the lidar approach, so laser scanner, together with a high definition map that is basically stored in the car. Again, the Waymo cars are equipped with camera, ultrasonic, radars, IMU, and GPS. But that's the main difference between level 2 and level 4. Level 4 only with camera will not work, while the other way around, the level 2 car, which is already in the market with lidar, is pretty much expensive, because the lidar technology is still pretty expensive, and it only works for we have seen the Audi A8 and the Mercedes S-Class. Those cars are much more expensive than a Tesla, for instance. They have a lidar in there because you still have to calculate some for one lidar, some I would actually say $7,000, 5,000 euros, but minimum that you need to put on your car on top, and that makes it pretty difficult for compact cars, for the compact car segment. Right. If we just have a short look on the timeline, what happened over the last decades. There was, let's say, a first very important project that started in the late 80s. There was a crossover project between especially Germany, France, and the US, the Prometheus project, that actually was the trigger for all the autonomy. Then it took a while, and one of the things was the automotive industry was not that interesting. And then DARPA, again, the military, like in many cases, came up with the so-called challenges. And the first one, 2004, was not very successful, while the 2005 Grand Challenge, and especially the Urban Challenge in 2007, they really were distributor and disseminator of this technology. And to be honest, 2007, the DARPA challenge, the Urban Challenge, was, let's say, the restart of this entire technology. And then we had in 2013 the Bertha-Benz Challenge, driven by Daimler, so Mercedes. 2014, the first version of the autopilot came to the market, and the projects of Waymo and GM started in early 2016, while we look at 2020 last year, and the same situation right now in September 2021. We have a couple of, let's say, providers, manufacturers that have level 2 on the market. It's Tesla, it's the Cadillac brand, Nissan, BMW, Volvo, the Audi traffic jam. So there are a couple of, let's say, cars which are not the cheapest ones that are on the market providing level 2. And if it comes to level, let's say level 4, it's a different story, and I'll come to that in a minute. If we, I think that's not that important. If you just have a quick look on the sensor suite, what kind of sensors are used, I think it's pretty obvious. You have, just open all together, you have different sensors. You have the long range radar, the short range radar, or medium range radar, the cameras. ultrasound. So you have a couple of sensors that are required to monitor the environment in real time. And that's the so-called perception layer, which is the most important one. It's safety critical because you actually need to know immediately if something is around your car. And the different sensors have different applications, as just drafted or shown here in the lower bottom of the chart to the right, where we see certain sensors are in charge for detecting pedestrians, other cars, traffic lights, be able to detect the lanes, which is pretty important. So that we need a couple of sensors. One sensor alone, just having the camera alone, would not work basically. And we have the Tesla approach. That's just too fast. So once back again, which is a level 2 car that is basically equipped with cameras. There is one front-looking radar, so one long-range radar in the front for the ACC. But Elon Musk and his team are mainly focusing on cameras because that's the cheapest sensor you can get for a car. The lidar-based approach is much more expensive. You have, in that case, the lidar, one big lidar on top, a spinning lidar, so that one spins around with 10 to 20 hertz. You get the data. You could actually use the lidar sensor, and I will show it in a couple of minutes. You can use the lidar sensor to localize your car. That means you don't need all the time GPS, or in other words, you could have GPS and lidar. You have some sort of redundancy. So if GPS fails, if you have no connection to satellites, the lidar sensor actually could take over and still calculate your position in world coordinates. Because in the end, that's one of the most important things. You always need to know as an autonomous car where you are. Otherwise, you cannot plan the next step, the next couple of seconds. You need to localize yourself. And it makes it a bit difficult because sometimes, like in tunnels, you don't have GPS. That's why you need a plan B or even a plan C if in case of certain sensors are failing. What happens right now in over the Atlantic in Europe? The Daimler actually came up earlier this year with the announcement. We have the S-Class. We have the S-Class of 2021, which can be already bought. The level 3 function, level 4 functions are deactivated right now, but they can be activated pretty easily once it's clear where the car is driving around. Now we know in Germany it's a bit easier, but if someone from France or from Austria buys the car, it has to make sure, especially Daimler needs to make sure that the level 3 and 4 function are really used in those operational design domains where it's legally allowed. And looking at the functionality, it's pretty simple. The L3 function is, as I mentioned before, just for highways. It's the highway pilot. It's limited, just talking about kilometers per hour, to 65 kilometers per hour, which means some 40 miles per hour. That's the limitation. You are not allowed to use the system for higher speeds. And for the level 4 functionality, it's only valet parking, only in a park house that actually is equipped with a vehicle to infrastructure, V2I, which is required. Then you could use this valet parking functionality. So you still see it's pretty limited. It's not level 4 as we discussed right before. It's just one function out of the level 4 world, and that actually means if you have an intermediate conclusion, level 2 is there. Yes, although if you really are more into in this, and if you own a level 2 car, you could easily stress the system. You could easily find use cases, scenarios where for instance, a Tesla autopilot is not working. If you have the, let's say, the right illumination, the right distance, if it's a foggy day, you will immediately see the camera is not able to detect, and then you have to take over as a driver. So level 2 is there. It's on the market. It's in the market. It's introduced, but basically it's the good thing from the car manufacturer's point of view is that the driver is in charge. and not the car manufacturer. That's why we can live with certain issues. And level 4 is still in development. Level 3, as I mentioned before, is pretty special, and to my opinion, it just makes sense on the highway. So it's, let's say, the question still remains, what to do if we would like to achieve level 4, and when do we see level 4? So that's our next question. And before we answer that, let's have a short look on the architecture, just to be on the same page. The typical architecture for an autonomous car, and I just have this, let's say, this architecture image that actually includes level 3, level 4, level 5. That's why we have to the upper right person, where I actually would like to highlight that we have driver monitoring, but let's focus a little bit on level 4. The first thing is we have a lot of situations that we have to capture. That could be, like to the left, a kid that suddenly runs in following a ball. It could be a really foggy day. It could be let's say a construction situation like we see to the right. So a lot of things that we have a couple of sensors, and those sensors, they are in place. So that's all what we have. And given those sensor data, we need to come up with, let's say, an environment model, a real-time capable environment model that gives us a 360 surround view with a special focus to the front view where we are driving. And given that fusion of the data, we actually need to understand what is happening around of us, what is the situation, and work out, let's say, do the reasoning and do the decision making. That means we have to decide, should we brake, should we continue driving, or should we evade, or whatever the conclusion is. But that has to be reliable and done in a robust manner, and that makes it a bit difficult. And of course, finally, we have the actuation. That means we have to accelerate, decelerate, whatever, to steer, to finally implement our decision. And in parallel, that's the blue box, we need to make sure that we always monitor our system. Are all sensors, let's say, all the hardware, is it running properly? Is there any degradation? Is there any issue? And from the hardware side, is the software running properly? That all has to be monitored in real time, and that makes it a bit more complicated. Just focusing on sense, plan, and act. So the sensor part, the planning part, and the actuation part is way too less focus. We need this blue box that gives us, let's say, an overall, let's say, degree of belief in the system. And if you look at this, let's say, this picture that I'm just sharing right now, you see that the different sensors are feeding different functions. And it makes it, again, a bit more complicated, because if one, so for instance, if one sensor, the camera, has a breakdown, it's just not working properly anymore, you see that a couple of functions are influenced immediately. And you have this interconnection, so you don't have this, let's say, this old school car functions. You have one sensor, one control unit, one actuator. So this very, let's say, clear, separated functionalities in a car, and all together. So all the functions, sensor function and actuation, all together assembled gives the overall functionality of the car. And in an autonomous car, you have a lot of interactions, correlations, and if one sensor breaks down, it's getting critical, because a lot of functions will not work anymore. And the other thing is that we have some sort of different time scales. The active safety, that means active safety in general means we have to avoid accidents. So in contrast, we have the passive safety. Passive safety measures, for instance, the seat belt. So we have a crash, and the idea is to reduce the injury degree. That's passive safety. Active safety actually means we wouldn't see a crash at all. And the active safety system have to work from 100 milliseconds up to 15 seconds. So active safety is one part, but the other part, which relates to Donges back to 1982, means we have different time scales. We have up to 10 seconds our mission level. So we are driving from Miami to Tampa, for instance. That's a planning on a high level. Then we have the tactical level, which actually means that's when we are driving on the highway, lane merging, bypassing another car, whatever. And we have the reactive level. That means if something happens immediately without any prediction, we have to react immediately on that. And that gives you another idea. We have a so-called mixed criticality situation. We have different timings that we have to deal with. And just pointing out one issue that we have, that's the diffusion topic. If you just rely on single sensors, we have a lot of drawbacks, like the limited range, performance is susceptible to common environmental conditions, range issues, and things like that. That's why autonomous cars always rely on multi-sensor perception, and immediately the conclusion is you have to fuse the data. And that's actually one of the agreed approaches, that you need to fuse the data from cameras, radar sensors, and lidar sensors to come up basically with some sort of hardware redundancy, but also software redundancy, in order to be more reliable and robust. And just very short, without going into details, one idea, or let's say one direct conclusion of sensor fusion, is that you actually can reduce the uncertainty. Like in this example, if we have sensors with different modalities, different physical principles, like here camera and radar, we actually could reduce the uncertainty, and that's one huge benefit. The other thing is related to that, and that's the example what I'm just showing, this small video. A car is just bypassing us, so the blue car is just coming along, it's bypassing us. That we have, let's say, if we have the car in the field of view where several sensors are detecting the car, we have basically very small variance. While if you only detect the car with a radar or with a camera, we have a very high uncertainty, a higher variance. And that's why it's absolutely important to fuse at least two sensors. And in the end, basically, it's either radar plus camera or radar plus lidar. That's pretty important to have, let's say, a more accurate feeding to the decision maker. And what has been done over, let's say, the last couple of years, also talk to the infrastructure. Because usually your lidar sensor, your long range radar sensor, sees roughly 300 meters. And that actually means that's it. Or if there is a car in front of you, you have a clear reflection. You cannot see through the car in front of you. But if you use data from the infrastructure and know from the Highway 101, for instance, in San Francisco to San Jose, or several places in Europe, or also around Clemson, you have a lot of infrastructure providers that already installed sensors that give data to cars if they request in the data. And that gives you, let's say, even you could double or even come up with a factor of 3 in range prediction. I just have chosen a very, let's say, quickly idea to give you, for those of you who are maybe not that involved in autonomous driving, what is the state of play right now. And that's just a typical implementation. You have a car like this. In that case, we have 3 lidar sensors on top. Let's say one in the center of the car and on the roof, and there are two additional ones at the back of the car. There are cameras in there. There are radar sensors, so 5 radar sensors, 1 long-range radar. It's visible just above the number plate, and the other 4 short-range radar sensors are hidden behind the bumpers or behind the back of the car. And that's a typical setup of a car, which is not Tesla-like, but it's a level 4 situation. As we said, Tesla currently is a level 2 car. The Waymo car or others from Ford or GM or Daimler are level 4 prototypes, and that's a typical setup of such a car. So you have a lot of basically sensors in there, and it's just the architecture. I will not spend too much words on that. The main thing is you see to the upper right of the slide where are the sensors mounted, because that's important for the fusion, because you need to make sure that you have the sensors aligned in 2 ways, temporally aligned and also spatially aligned, in order to avoid that you are fusing wrong time instance. So that's pretty important in the sensor fusion way. Just running a Kalman filter, that's not the right approach. The Kalman filter is important for sensor fusion, but you need the temporal and spatial alignment up front before you run any algorithm afterwards. And this, let's say, these videos to actually show you what, if you focus on lidar-based localization, first thing is you need to drive around and create a static lidar map. That's the first thing. This lidar map is then stored in the car. And if you then drive around this part or this region where you have already created a lidar map, a static lidar map, then you could do actually a match between the new data, the new point cloud data of the lidars, and then with smart algorithms, localize yourself within centimeters. So that's a great approach. You can do that, of course, with differential GPS and with a HD map. That's the different approach. Right now, this LiDAR approach is a bit the cheaper one because differential GPS are, just to give you an idea, they cost you some $20,000, so pretty expensive there. But you can achieve, again, some centimeters of accuracy. But basically, and I'm just running this video once again, is what you actually do if you focus on lidar-based localization. First, you need to calibrate the lidars. So whenever there is a 1 in this list, then it's to the left video, and the 2s are to the right video. So we need to load our map that we have stored. We have, in our case, 3 lidars. You have this normal distribution, transformation, localization, and a couple of steps like the voxel grid filter that and the point cloud transformation. Because we have 3 point clouds, we need to transform them then to 1 frame. So that there are a couple of steps required in order to finally get your position. And the cursive, so 3, let's say those are right now here. So if we just continue watching this video, we see in a second that we have done the ray ground filtering. So just cutting off the ground because the ground is there, so we don't need to process the data of the ground. And the same thing at a certain height, some 5 meters above of us, the data is not very helpful for generating a trajectory. And then we come up with the clustering that's happening right now in the video. And finally, we are fitting boxes, and those data of these boxes are then used to do the sensor fusion and also to plan the next steps in your trajectory. So that's the typical way, and that's summarized here once again. You come up basically with the global planning, so that's from A to B, and we need to work on the local planning. That's the lower level, the reactive level, where what happens if a pedestrian steps in, we need to immediately find a way to the right decision, and always braking might be not the right decision. And usually you are calculating some 10 to 15 trajectories as shown here. In a different color code. Red means it's not allowed to drive this trajectory, while green means that's a good one, and yellow means it's allowed, but actually it's not the best trajectory at all. And the other thing is where the cameras are used. Cameras are basically used to classify our objects around us, like you can see here, pedestrians, cars, trucks, traffic signs. But actually is another layer of information that comes in that also feeds our fusion layer to do the right decisions for the next couple of milliseconds and seconds. And one example that I'm showing here is autonomous racing, which Julie just briefly mentioned at the beginning. There is, let's say, a great racing series located in Las Vegas. So the headquarters of RoboRace actually is in Los Angeles, while let's say all the races are currently done in Las Vegas. And the idea is for currently 7 teams, including MIT, Carnegie Mellon University. It's us, it's Pisa, it's Milano. So it's so let's say teams from the US and from Europe are competing. Only on the software. The hardware is the same for all the teams, so it's the same racing car, and to just load your own algorithms on the car, and of course the fastest cars in the end is winning. And it's up to you which kind of sensors you're using and which kind of sensors you're not using. That's up to you, but it's a great thing, and we will have that. And that's just a bit of advertising. We will have in March next year in Austin, Texas, the South by Southwest festival, and RoboRace will be there along with other exhibitors. But we will have a race downtown in Austin where hopefully I'm also there with my team, and hopefully get a good, let's say, a good result there when we are running in the city of Austin. That's just a bit of an idea, and just giving, this slide might be maybe too far, let's say, way too deep for the discussion today. But actually, the difference between passenger cars and racing is you have different dynamics, you have different speeds that you have to deal with, and that makes it much more interesting to do the sensor fusion, because it has to happen in a lower, let's say, in a lower range of milliseconds, while in the passenger cars you always have this 100 milliseconds, which are typically sufficient. That's just the way. But just coming to the next part, which means why don't we have self-driving cars yet? The thing is, software. We have the issue that autonomous cars consist of a lot of software, and software, the software process or software is always late. That's a typical thing in car manufacturing. And if you just have a look, this example that I brought, that compared to the, let's say, F-22 or a Boeing 787, the code, let's say, line of codes in a car, they are really exceeding any limit, and checking the software, making sure that software runs properly is an incredible, crazy thing. And the other thing, what we actually have is this 90-90 rule between technology and time. That actually means, just showing in a second what it means, that right now in our level 4 world, we actually have, let's say, within, would say, 10% of time, we got 90% of our technology, which is good, but the remaining 10% that are needed to get those level 4 cars in urban areas, that might take very, very long. And in the worst case, it's the 90-90 rule definitely could apply, let's put it this way. So that means it will take us another long run, a long shoot, that we get, let's say, this readiness of the technology that is then let's say, accepted by the market, accepted by the end user. And the other thing is, do we need 100% or are 18, let's say, 98% sufficient? That's another question. And actually, the thing is, for autonomous driving, the overall goal is we need to show that those cars are better than we. So we as human drivers set a very high bar, but the technology has to show that the cars are even better, and that's pretty difficult, because showing that the reliability is just a small calculation that I'm showing here, close to 100%. That's a crazy thing that it's almost infeasible to achieve that. And in the end, right now, the approach is always that autonomous cars have to reduce the number of road fatalities, and there are nice simulations, calculations, but in the end, we need to come up with a so-called acceptable risk or residual risk, like we always have. And just to give you this example that has been basically brought a couple of times, I just decided to show it you once again. It's for level 2, it's the same thing. If you were just choose Malaga in Spain as a home base. If you're located in Malaga and you would like to climb the Mount Everest, the highest summit in the world, 98% would actually mean you fly over to Kathmandu, so you're almost done. But basically, the final 2% to climb the mountain, to climb the Everest, they are the most critical ones. And that gives you a bit of the idea that level 4 means we have 98%, that's fine, but the last 2%, those are the most critical ones, and they are important to show that those kind of systems are reliable, and we can trust in those kind of technology. Otherwise, no one will buy such a car if you don't trust technology. And this slide actually shows you a bit of where are the challenges right now. The blue boxes show you a little bit the technology that has to be advanced. You see the sensors, it's still an issue. how to deal with AI. Just show you quickly next slide where the AI topic comes in. Detecting the environment, coming up with the environment model, how to involve the driver, how to warn the driver, how to, let's say, include 5G or maybe 6G in the future. What about the latencies? That's another issue. This is not, right now not solved. And finally, how to assess the safety, security, and reliability. And that only has a chance if we agree globally, at least those countries where car manufacturers are located, on, let's say, on test requirements, on scenarios where we have to test against. And that's one of the things which is pretty important. And if you look at AI, just bring it this way, the end-to-end approach that has been discussed in 2015, especially by NVIDIA and many others, that's the one that is not feasible anymore, that you just train a neural network, you get your sensors, and you have the steering wheel angle on the other side, and the huge network in between, that's just unsafe. And currently you have this approach that whenever it comes to collision avoidance, AI is currently not allowed, and that will not change over the next couple of years, because AI is currently not fully understood. You cannot formally prove that the AI is reproducible, that the different layers are activated in the same way. That's why you always have this deterministic pass, this parallel pass, this bypass called the safety pass. There and companies like Waymo, and I keep it short right here, they come up with very nice slides. And if you're a bit more interested in that, I put the web link down there. That's not Waymo, it's Aurora. Sorry for just mixing up. Aurora is well known in the US for, so Chris Ehrman for the safety stack. And one of the things is, as I said before, software is the main driver. We are talking about software-defined vehicles. And if you cannot prove that the software is up to date and the software is working properly, you will not have a chance for level 4 at all. And if you just visit this website, you will see, and you could actually, for all of these global, let's say, general goals, G1 up to G5, what is the approach of Aurora to really prove that, those kind of things. Yeah, and one of the things, and I'll keep it again short because it's anyway recorded, the issue of the corner cases or rare cases. That actually means we can test for a lot of cases. You will never manage to test against all scenarios that might appear. And unfortunately, we do not have a Gaussian distribution when it comes to the scenarios. We have a lot of scenarios that we can deal with that can easily be tested. But in the long tail, and that's why we talk about heavy tails, you have a lot of cases, scenarios in the so-called tail of the Gaussian distribution. And the worst thing is that you have almost 50% in the tail and 50% where you usually test against. And that makes it a bit critical. And I just took this the slide, or adapted the slide of Phil Koopman from Carnegie Mellon University, who is a really great guy working on, let's say, on functional safety and safety of autonomous driving. And he was the first who came up with this heavy tail distribution, and they make sense because what I added here is for pedestrian accidents. If you just assess your system for, or in the other way around, only 26 different causes of accidents result in 50% of the overall accidents. Here we are talking about pedestrians coming from the right. But the remaining 50%, there are 5,287 different scenarios, and finding out all those scenarios, even for level 4 for cars, that's just infeasible. And that's where we are currently sticking, and that's why the ODD, the operational design domain, is pretty reduced to, for instance, only highways, for instance. And if you see in the US cars driving around, or in Europe, it's always a safety driver in there. It's most of the situations is learning, collecting data, and hopefully improving the system. So that's what it is. And I'll skip this one because I think the most important thing is right here, when I, let's say, going to conclude my talk, actually is we have, let's say, no level 4 function officially in operation. It's not there. They're just prototypes, they're just demos around the world. We are working on that, and hopefully we'll see solutions over the next couple of years. Level 5, as I explained, is basically an infeasible situation, and all the manufacturers around the world meanwhile know that level 4 is, so level 2 and level 4, that has to be focused. And we have a couple of issues that are just we have it just written here. I wrote it here, that we have to prove reliability and robustness in a, let's say, reproducible way. We need some sort of redundancy concept, and we cannot take it over from the avionics, because triple redundancy is just too expensive for the automotive. We have to decide what kind of data should be processed in the car. So people will say the edge is the car, edge versus cloud. So what can be done in the cloud? What can be done in the edge in the car? That's currently it's research, so it's not the solution out there. That has to be calculated or computed in the cloud, and that's just not yet solved. And as I already mentioned before, we need a set of harmonized scenarios. Finally, we need to say, if the autonomous car checks those scenarios in the US NCAP or in the European NCAP or the Japanese NCAP or whatever country we are talking about, if the car passes those tests, then we are sure, and we are definitely in favor to see that car on the road. So that's still in progress. So it's not yet there. And what you can see here is, if you just, and the scale is different now. So we talk about 2030, and if you look about level 4 in 2020, we started with, let's say, valet parking. That's something which is not very, let's say, fancy. Valet parking is nice, but that's where we are currently having the solutions because of the safety issues. Valet parking, that's the cool thing. It's low speed, and it makes things are easier. And if you talk about urban driving, it's still on the agenda of all the car manufacturers. But as you can see here, we are talking about some 8 years ahead of us. That gives it a bit, let's say, it gives us a bit of, okay, now we are in 2021, close to 2022, but we still have to wait some 7-8 years to see, or let's say to buy such cars when they are level 4. Of course, we will see cars that have level 4 features, but right now we will see, and that's not that bad, because the benefit of what we have seen as let's say as customers is that all cars around the world, all brands, they have improved in terms of safety. So all the active safety systems, they are meanwhile great. So cars are much safer now, thanks to the autonomous driving hype, because many of the functions that are necessary for autonomous driving can be used for active safety. And that's, let's say, to be honest, a very great step, that we have increased the active safety, the safety of the cars. We have already reduced the number of road fatalities in all countries in the world that are participating in autonomous driving. It can be easily found in the internet, that we have great success when it comes to safety increasement and improvement and decrease. And of course, we will still see a stepwise approach. We will see level 3 features on the highways, which are a bit more comfort functionality, and stepwise we will see level 4 functionality. And that's, sorry to say that, that's the, let's say, a bit the slow and evolutionary approach, and not the revolutionary approach that we actually expected back to 2015. And having said that, I would like to conclude my talk, and thanks for the patience, because I took a bit longer than expected, and I'm happy to answer your questions.
Thank you so much, Daniel. It looks like we do have a number of questions in Q&A.
So I think I should just open the chat. So we start from.
Are you seeing the Q&A function?
Yes, yeah. So the first one actually is, as I understand, level 2 autonomous cars rely on camera. How many % of accidents are due to contamination of camera? Yeah. So the first, it's a very good question, because cameras for level 2, as I said before, level 2 means always that the driver is in charge. And if you activate the highway pilot, or if you use the ACC, you're always in charge. That's the first thing which is important. But right now, camera systems, if you just to bring up one example, traffic sign recognition. Traffic sign recognition is by 95%, so we still have 5% to go. That means in 5% of the cases, the camera is detecting something, and in the worst case, it's just telling the camera is not working. So if you own such a car where you have those functionalities, you might easily find situations where the camera just is not able to give you an answer. ACC, there are a couple of cars that that built ACC, so adaptive cruise control with a camera, but meanwhile most of the ACC equipped cars, they rely on the radar sensor, because the radar sensor is much more reliable when it comes to depth estimation. A camera alone, if you have a mono camera, is not able to work out the distance. You always need a stereo camera to work out the distance, but cameras are, that's the final say to that. They have issues when it comes to nighttime. So if you have no daylight, and the other thing, if you have rain or snow, or let's say really those kind of weather situations, then the camera is not working at all. So that means just having the camera, like the Tesla approach, that works quite well in California, Arizona, and so on, but it might not work in Sweden or in other countries where you have to deal with those kind of weather conditions. I hope that answers your question. The next one actually is, so where it is. I'm assuming all lidar applications proud of, just reading once again, I'm assuming all lidar applications proud of the car. Has, I got it. I think the question is, are the lidar sensors always external, so on the roof or somewhere else? No, actually not. So there are different ways. Let's say the most easiest way is to put it on the roof if you have a prototypic application, and that's why Waymo is still doing that. But if you look to BMW or let's say other car manufacturers, they have usually 3 to 5 lidar sensors, let's say mounted to the left and to the right of the number plates, to the front and to the rear. So it's there are approaches where you have the lidar sensors integrated into the car. So next question is from Selim. What do you think is the role of the infrastructure support in terms of achieving high levels of autonomy? So my opinion is we need the infrastructure. Without the infrastructure, it will not work right now. And I think we spent a lot of time in just doing research and development on the ego vehicle, just focusing on our own vehicle. We now start to think in multi-agents. It means that there are other cars around that might be autonomous, that might be standard cars, and without talking to the infrastructure, autonomy, especially in urban areas, will not work. So that's my own opinion. Then we have the next one. Will the sensors you presented function as expected in extreme weather conditions? For example, there is 10 centimeter thick of snow on the ground and it's snowing. To make it worse, the electricity power is down. In other words, no network is available. Yeah, that's of course a tough one. And you could imagine that this kind of situation is one of the corner cases that has been already identified for several years. And to be honest, it's one of the things which is right now not working. You might find videos from demo cars, especially from Volvo, that show that it's working. But actually, radar is working quite well when it snows and when we have heavy rainfall. But as soon as we have, let's say, metal guards and so on, then radar is not working anymore. But radar is pretty pretty, let's say, reliable when we have those kind of weather situations you just mentioned here in your question, where lidar sensors typically have their issues when there is let's say heavy rain and heavy snowfall. And if we have, let's say, snow, some centimeters of snow on the road, it's getting even more critical. But that basically is exactly what Selim asked. Here we actually know, and we need to know, let's say, information, and we need to get and receive information from the infrastructure. Otherwise, those kind of situations will not work. Then autonomous cars will not be able to drive around because sensors are not that mature that we actually would like to see. And if you said the scenario is even worse, no electricity, that means, I guess you mean no infrastructure communication. Then actually, as we have 2021, it doesn't make sense that the car drives around autonomously because it's just too unsafe. If you have just to rely on your sensors, and of course, the overall approach that always will work is that you just reduce your speed to 5 kilometers per hour. But then we are in a situation where people start to ask, what is the benefit of such cars if they are so slowly or just in the same speed than pedestrians? So another question is there any ready-made stereo cameras are available in the market to directly calculate the depth of the preceded vehicle? Yes, that's on the market. So you even can find and buy cameras that have, let's say, three lenses. Autoliv, for instance, a company from Sweden, a supplier, Tier 1 supplier from Sweden, is offering that one. So you definitely will find those kind of sensors that are able to calculate the depths of, let's say, of the preceding car. The more expensive approach is to buy, let's say, the camera of Mobileye. Mobileye is, I would say, the leader in the market. They have a different approach because they actually use artificial intelligence to calculate the depth, or let's say the distance to the next car. There's a, let's say, very sophisticated algorithm. The only thing is you always have to, you need a relative speed, then it's working. If it's static, so if you're stand still, then the sensor is not able, because you always do some sort of moving average. So you need average over different frames. So that would be the expensive variant to buy a Mobileye camera. Of course, there are different let's say different variants of Mobileye, but if you just look for a stereo camera, including the algorithm, you will find it in the internet. So
there are some additional questions in Q&A. It's a different icon on.
Yeah, got it. So first one is adapting a new technology is difficult when users fear for their safety. Yes, true word. What annual vehicle certification? So yeah, got it. So what will be the annual, or let's say the certification, what we usually know right now for every single year, you have to do that, or the recertification. Yeah, it's a very good question. The one thing is that we have, let's say, different approaches. The US goes for the self-certification approach. So the first step is when such cars are allowed to enter the market. The US is different to the European Union. Self-certification versus homologation. Self-certification means you don't need a third party to check if all is there. You just have to prove and make sure that all is in place. In Europe, it's different. You always need some sort of a legal, let's say, a third party that is checking if the car is safe to be, let's say, to enter the market. So that's the first step. And then, of course, that's your question, Dr. Zafar, is how will be the annual update and how will the recertification will take place? And I actually would say it's, to be honest, it's of course discussed, but it's a problem that it's, or in other words, there are other problems to be solved earlier. For instance, if there is an accident with an autonomous car, how to make sure to have all the sensors been mounted properly. What happens if in the production the sensor is 1 degree, the radar sensor 1 degree to the left or to the right, or upwards or downwards? Those kind of things are currently not yet solved. How to prove and how to make sure that this, let's say, this uncertainty in manufacturing can be certified. So that's where currently the different bodies around the world are working on. And I think this problem that you're mentioning, that there is the need to come up with something like that. Yeah, but as you might know, even the workshops they don't have the, let's say, the skilled resources, the skilled persons to do that right now. So that's one of the things where we are a bit, let's say, have to look a bit far in the future. Then again, from you is, will you be looking for redundancy for fail operation and fail safe? Yes, so that's important. There are certain ISO norms already in place, the ISO 26262 and the safety of the intended functionality, SOTIF, that are already in place, where you have to prove that your system, if it's, so you have 4 levels. They are called automotive safety integrity levels, A, B, C, and D. And if you, for instance, steering and braking is always D, so the highest safety integrity. If you have a system like that, or perception is D, localization is D, then you have to show that your system is redundant. That means fail operation. In other words, if you do it fail safe, as I say, fail safe is one of the things which is maybe not the best solution. Fail safe actually means shutting down the system, and that's in certain situations not possible. Then you have to be fail operational. That means you have to continue your drive, even if you degrade your functionality, but at least that you drive to a safe bay right to the street or something like that. But that's a big requirement, and fail operational behavior is on, even in the standardization, it's on the table. So that's where things are already there. And if you look at the Daimler car, that is already out there, and that has fail operational behavior, for instance. And what is the difference between ACCD and AC? Why do we require ACCD? Yeah, I would put it this way. It's, of course, ACC is standard, the adaptive cruise control. That's the one which we can buy. While ACCD is, let's say, an advanced functionality. If it will be, let's say, always available in cars, that might be questionable. But in fact, let's say, autonomous cars, or let's say the car manufacturers, are basically looking at their business models a way like mobile phones are working, that you have certain applications, certain features that you can download, that you can use, or you have to pay for it, of course, or you just keep it as this, and you say you don't need this functionality, and to save your money. So I don't think that we actually, ACC is required, of course, that will be a standard functionality, while, for instance, ASCD might not be important at all, or standard situation. Then we have, how do you assess the influence of IoT architectures and the edge to cloud computing technologies evolving on the autonomous engineering with respect to faster using GPU and reliable response? Yes, that's definitely a great question. Right now, the automotive industry is that's just the way automotive works, pretty conservative. For the last couple of years, the focus was to have a GPU in the car to calculate and to compute everything within the car, and don't, let's say, talk to the outside. Meanwhile, it's pretty clear to run everything in the car could be done. It's then technically feasible, but the price of such a car will just, yeah, it will not be affordable for the masses. And that actually means we need to outsource certain calculations to the cloud. So that's let's say the starting point. On the other way around, if we just look at 5G, which is already rolled out not everywhere in the world, but in cities or in certain countries, we have a good overlap on 5G. But we also know cars need to share the 5G bandwidth with Netflix users, with any other, let's say, yeah, application that uses 5G, and that actually means the latency, let's say real-time response, might not be guaranteed. And that brings us immediately to the conclusion that if we talk to the IoT, or if the car is let's say an IoT device, we need to make sure that only, as I said before, ASIL A and ASIL B functionality are outsourced to the cloud, because then we don't have, let's say, the safety critical and time critical demands, while ASIL C and ASIL D functionality, but it will not change anyway, have to be calculated in the car, on board, in vehicle. But it's definitely, it's a matter of research. What can be calculated in the cloud? How can we ensure that we have deterministic behavior in the transmission of the data? And let's say in all the test fields and proving grounds, it's easy to show that it works. But my personal opinion is, if such a car drives at, let's say, in 6 p.m. in New York City, where a lot of people are already at home watching Netflix and doing a lot of stuff in the internet, then we need to come up with a different protocol within 5G that reserves certain bandwidth for autonomous cars. But that's again like a chicken and egg situation. Once we have more autonomous cars, that might happen that the mobile providers reserve that kind of bandwidth for such cars. So that's just my opinion to that. The next one is, looks like auto testing verification technicians, we need apps and have some exposure to IT business. Is that right? I guess yes, I think so. Yeah, I'm in line with that. What you're just writing here. The IT business will play a very important role, and I think I mentioned this term, the software-defined or software-enabled vehicle, and that actually means that software and IT business in general will play an important role in the future if the ecosystem increases in terms of autonomous driving. And there is also, have we looked into remote testing verification of the vehicle characteristics using RF links? I'm not fully sure if I get this point right. Let's say my interpretation would actually be that right now many car manufacturers test the cars on site. So the cars are just down the engineering offices, and you just go down and do the testing, or you go to the proving ground, which is quite close to the company. And your question might actually focus on, is it possible to do the testing if the car is somewhere in the world, in a different site, in a different country, different time zone, although the engineering people are sitting in a different place. I'm not sure if I get it right, but if that's what you're focusing on, that's already in progress. And the best example is RoboRace, what I briefly mentioned. The cars are all in Las Vegas. The software is developed in Boston or in Graz or in Pisa, so in different places in the world. Then we usually Dockerize it, so put it in a Docker, upload it, and the guys from RoboRace are downloading the software stack, so they enter a DNA of the car and put it to the car. And then there are some safety tests if everything runs smoothly and correctly, and then the car can actually be started and run with the software that has been developed somewhere else in the world. So that's one of the things which gets more and more important, to have this, let's say, verification and testing, although the car is somewhere in the world. I hope I got this question right. Yeah. Right. And I think, I'm not sure if Julie, did I miss anything?
I believe that that is all of our questions. Thank you so much again.
You're welcome. Thanks a lot, Julie.
Bye all.